Think of a car journey. Your distance from home is a function of time. As you travel, your speedometer tells you exactly how fast you are moving at any single, precise moment. That speedometer reading is the derivative. Mathematically, it is the slope of the tangent line at a point on a curve, representing the instantaneous rate of change. The power rule is the cornerstone of differential calculus. Whenever you encounter a simple power function, this rule allows you to find the derivative instantly. Consider x to the fifth power. According to the power rule, we bring the exponent 5 down to the front and reduce the power by 1, resulting in 5x to the fourth. This simple process is the foundation for analyzing the vast majority of polynomial functions you will face in your calculus journey. The product rule applies when two functions are multiplied together, such as x squared times sine of x. We treat this as a partnership. First, identify your parts, u and v, then find their individual derivatives. In the partnership, derive the first and keep the second, then keep the first and derive the second. Add them together for the result. When dealing with one function divided by another, we use the quotient rule. It is essential for finding the rate of change in fractional relationships. The formula is the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. Think of your function as a fraction, where the numerator is u and the denominator is v. Order is critical here because of the subtraction in the numerator. The numerator is u prime times v minus u times v prime. Always ensure you start with the derivative of the top, as the negative sign makes the order non-negotiable. The chain rule allows us to differentiate nested functions, which we can think of like peeling an onion. To differentiate f of g of x, we differentiate the outer layer while leaving the inside untouched, then multiply by the derivative of the inside. Visualize your function as layers. The outer layer is f, and the inner layer is g of x. Let's apply this to the function 3x plus 2 chord 5. We treat the power of 5 as the outer layer. Bring the 5 down and subtract 1 from the exponent, keeping the inside exactly the same. Now we multiply by the derivative of the inside, which is 3. Simplifying this gives us 15 times 3x plus 2 is squared. This is the power of the onion method. Peel back the layers, multiply the inner rate of change, and you have successfully applied the chain rule. To master derivatives, use the PPQC memory map. Start by identifying the function structure through this decision tree. If your function is a simple power of x, use the power rule. If you have two separate functions multiplied together, use the product rule. If your function is a fraction, reach for the quotient rule. And if one function is nested inside another, the chain rule is your key. Follow this map. Identify the structure first, then apply the rule. This is the foundation of mathematical modeling. Derivatives are the hidden engine of modern AI. Through backpropagation, neural networks use the chain rule to calculate how every single connection contributes to an error, allowing the system to adjust and learn. In finance, derivatives are used to manage risk. Known as the Greeks, these measures calculate how portfolio values shift in response to price changes or volatility. It is calculus that provides the sensitivity analysis needed to secure global investments.